Hi, welcome to the video walkthrough of the ordering question. And the question first asks us to provide a definition for each of the bounds below with your own word. So first up, we have big O notation. Big O notation provides an upper bound on runtime of a function as the input size approaching infinity. So if we have a function fn, the order of the growth will just be like less than or like equal to fn. So big O notation give an upper bound on the runtime of a function as the size of the input approach infinity. But you have to mention that the big O is not same as the worst case bound. So rather it gives us an upper limit on the runtime for any input size. This means it's describe a boundary that the runtime will not exist. But it doesn't necessarily specify that this boundary is achieved only in the worst case scenario. In some cases, the actual worst case runtime might be lower than the upper bound provided by Big O. And next, we have lower bound, which is big omega. So imagine we have a function fn. The order of growth is just bigger than or like equal to fn. So big omega notation just give us a lower bound on the runtime of a function as the size of the input approach infinity. Just similar as the big O notation, is not same as the best case bound. And finally, we have this big theta bound. So same for the function fn. If we have big theta of the function, it just means the order of growth is exactly fn. So big theta notation just gave us an tight bound on the runtime of a function as the size of the input approaches infinity. And this means like the upper bound and the lower bound is just exactly the same. So we just use the tight bound to describe the order of growth. Let's move on to the next part. Find the sum of the following progressions. So the first expression is 1 plus 3 squared plus blah 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 plus 3 to the power of 50. So if you look at the context provided in the question or like specific constraint that indicate like dedicate like considering only the largest term, which is 3 to the power of 50. It turned out that in the grand scheme, like perhaps comparing to other terms or like scenarios in a larger system, for example, if we have 3 to the power of n and n just approaches to the infinity, it is much more considerable than the 3 to the power of 50. So this value is just constant relative to other function or terms being considered. And also, as you can mention, like for most of the asymptotic problems, we have like input as n and the n will just approaches to the infinity. But here we have the input as 50, which is a constant. So overall, the order of growth of the overall expression is just in the constant time, and we just express it as a big theta of n. And for the second expression, the way we can solve it is just separate this expression to two halves. So we have first part as 1, and the second part is just the rest of the expression. We have 1/2 plus 1/4 plus 1/8 plus blah blah blah. And we can just rewrite this expression as the sum of I start with 1 and approaches to the infinity. And the general term is 1/2 to the power of I. And if you drag the I of different number into expression, this will just give you the expression as 1/2 plus 1/4 plus 1/8 plus blah blah blah. And the sum of these numbers is just 1, or like 1 minus 2, 1 over 2 to the square to the power of I. And you can think of like a square whose area is 1. So imagine we have a square S and the area of S is just 1. And we cut the square to two halves, and we have 1 over 2 for the left part, and we just keep cutting the rest part into halves, and then we will have 1 over 4, and we just keep doing that. We will have 1 over 8 and 1 over 16, and we just keep doing that. And finally, there will be only like a little square whose area is 1 over 2 to the power of I left, and we just add the rest of all squares together, and the overall area will be 1 minus 2 to the I, 1 over 2 to the power of I. And since I approaches to infinity, so the area would just be, so this would be 0, this would approach 0, and the overall area would be 1. So the sum of this series would be 1, and we add this one back to another one, we will get to, which is just a constant, and we can simplify it as the big theta of 1. And for the third expression, we have 1 plus 5 plus 10 plus 15 plus blah 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 plus n squared. And it's just like if you split it to 2 parts. So for the first part we have 1, and for we just have all the rest in another part. You can see this is just a arithmetic series. So for the arithmetic series, if we have, for example, 1, 2 plus 2 plus 3 plus blah 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 plus n, we will just have like the big theta of n squared as our order of growth. And the point is the last term. So we always take the square of the last term as our order of growth. So in this expression, we have n squared as our last term. So we just take the square of n squared, which is, square of n squared is just n to the power of 4. And then we add the 1 back, which is just a constant. So we only consider the larger part, which is n to the power of 4, as our sum of this progression. So we have big theta of n to the power of 4 as the answer of the third progressions.